All right, so I just hit record. So what I'm going to do here is I'm going to share my screen. And let's see, I'm going to share this screen. So hopefully you can now see, I think the Top Hat window should be up right now. And what I'm going to do is respond to a question that Heather posed, which is, in modeling environmental stochasticity using a normal distribution, it starts out, she's asking, does it start out like an uncertainty analysis in that you have an upper and lower bound, but then you take the mean of those bounds or the variance, and that's what you apply to the normal distribution? And I think really what we generally have, and I'm going to move over to R here, what we generally have is more like a set of data that we're fitting. So when we're actually trying to like understand and model environmental stochasticity, ideally we have some data behind that to allow us to better understand how variable our system actually is. And so here's an example where we have survival rates, and it could be birth rate, it could be, hatchling survival, or it could be any vital rate that we're interested in. But ideally we have data, and this is what I'm thinking about here is annual variability. And that's often what we mean by environmental stochasticity. We're talking about annual year-to-year variability. So let's imagine we've collected data on a population for multiple years, and we've estimated the survival rate for 8 years, say. And so we have these are our data. We have 0.8 survival in year 1, which was 2001, and 75% survival the next year, 91% survival the next year. So we have good years and bad years, and that's really what environmental stochasticity is all about. So let's read that into our R session. And I'll just name the survival rates. So hopefully, I haven't tested this yet, but you see now we have survival rates associated with each year. I'll make this a little bigger so you can see it better. But you'll see that I have, for 2001, survival rate of 0.8 and so on and so forth. So now I have some data to work with. And so, really when we're fitting environmental stochasticity, we don't just have a minimum and a maximum value. We have a whole bunch of values. And what can we do with those? Well, we can compute the mean of those values. So let's compute the mean. I'll say mean served, and I will assign that to be the mean of my survival rates. And so it turns out, let's look at it, mean served, it's 0.835. So that's the mean of the survival rates that we estimated for this population. Now, the normal distribution is described by a mean and a standard deviation. So we already have now one of the parameters for describing or for constructing this normal random number generator for survival rate in this population. Now we just need to compute the standard deviation. So I can make a new variable, standard deviation of survival, and I'll use the SD function, which is in R, going to calculate the standard deviation from the data, and I will just feed in the survival rates. And so now I have standard deviation serve. Standard deviation in survival rate in this population is basically 6 points or almost 7%. That's saying that the mean is 0.835, but there's some variability such that anything within about 7% of that mean survival rate is somewhat likely to occur. And anything within 2 standard deviations, more like 14% of that mean, is possible, we might observe. So let's fit a random number, or let's construct a random number generator, a normal random number generator. Can use distribution, and we take the mean survival rate and the standard deviation of survival, and the first parameter there, of course, is the number of random numbers we want to generate. So let's generate 5 random numbers out of that distribution, and there we go. So you're going to get something different because this is a random number generator. but I get numbers that are basically centered around 0.835 and have some variability that are associated with that standard deviation. And if I wanted to just look more carefully at this, I could, let's generate 500 random numbers out of this. If we save those, my random numbers, and make a histogram, we can see that we get, you know, if you take all these random numbers and make a histogram, it looks like a normal distribution. It's starting to look like a normal distribution. So that's how we can fit a normal distribution to data that we have on our population. You could fit a uniform random number generator like you were mentioning. The random uniform just takes a minimum and a maximum. So I could make a uniform, our uniform, take 500 of those. And instead of using the mean and the standard deviation, I'll just take the minimum of my survival rates and the maximum of my survival rates. Those are the parameters that describe a uniform distribution. And then I can plot a histogram again. And now it looks like a uniform distribution. So I could fit a uniform distribution to these data, and I could fit a normal distribution to these data. It's my choice as a modeler which distribution makes more sense in this case. And I think probably a normal distribution makes more sense in this case, but it's up to you as a modeler. All right, I will sign off there, and I will post this recording to Top Hat if I can figure out how to stop this.
There we go.
And I will stop video. No, that's the video setting.
It does still look like it's recording.
It is recording, and I can't stop it. Oh, there it is.
I have a, okay.